Look at this image grid. It's the MNIST dataset, a collection of handwritten digits ranging from 0 to 9. Our goal is to build a neural network that can evaluate any one of these images and accurately classify it into one of 10 distinct categories. Up until now, we've looked at models that make simple binary decisions, like determining if an input is positive or negative. Here, the network has to choose between 10 different possible outcomes. In a standard binary setup, we rely on a single output neuron using a sigmoid activation function to give us a probability. But a single neuron toggling between two states does not have the mathematical capacity to represent 10 mutually exclusive classes. To solve this, we shift to multinomial regression. Instead of one output, we design an architecture with 10 distinct output neurons. Each neuron will compute a separate probability for a specific digit. To generate those individual probabilities, we use the softmax activation function. As you can see in this equation, softmax takes the raw output of our 10 neurons and maps them to a range between 0 and 1. Because the denominator normalizes the scores across all neurons, the 10 outputs will sum exactly to 1. Once the network makes a prediction, we measure how far off it is from the true label. For this, we use the cross-entropy loss function, which minimizes the negative log of the predicted probability. Let's look at the math in practice. If the network is highly confident and predicts the correct class with a 0.9 probability, the negative log yields a very small loss of 0.105. But if it guesses the correct class with a tiny 0.01 probability, the negative log penalizes it with a massive loss of 4.61. By heavily punishing low-confident correct answers, cross-entropy loss forces the network to push the probability of the correct class as close to 1 as possible. Before we pass any images to the network, PyTorch's data loader prepares them. It normalizes the pixel intensities, groups them into mini batches of 32, and shuffles them to prevent the network from memorizing the specific order of the dataset. This diagram illustrates our next hurdle. Our input data is a two-dimensional 28 by 28 grid, but standard dense neural network layers expect a one-dimensional array of numbers. We solve this by flattening the image. We unroll that two-dimensional grid into a single vertical column, transforming the image into exactly 784 numerical features. Now we can feed those features into a multi-layer perceptron. This schematic shows our complete architecture: an input layer, 2 hidden layers, and our 10-unit output layer. Every single one of those 784 input units connects to 512 distinct neurons in the first hidden layer, mapping the raw pixels to complex patterns. Without that initial flattening step, we couldn't bridge the gap between two-dimensional shapes and the dense mathematical layers required to process them. When we code the training loop, PyTorch has a specific quirk you need to account for. The built-in cross-entropy loss function automatically combines both the log softmax activation and the negative log likelihood loss into a single step. Because PyTorch bakes the activation function directly into the loss calculation during training, what do we have to do manually when making predictions on unseen test images? We have to apply softmax ourselves. During inference, we don't calculate loss, so we must manually pass the raw network outputs through a softmax function to get our final probabilities. Understanding how your framework handles activations prevents mathematical errors, like accidentally applying softmax twice during the training phase. This chart tracks our model over 5 training epochs. Accuracy steadily climbs toward 1.0 as the network updates. Notice the blue validation curve. Its close alignment with the training data proves the model can accurately identify completely unseen digit samples. Let's test it by passing an entirely unseen image through the trained network. Here is a sample from our validation set. The network evaluates the flattened pixels, and the output neuron assigned to the digit 2 fires with a 99% probability score, leaving the other 9 classes effectively at 0. By flattening inputs, setting 10 output neurons, utilizing cross-entropy loss, and managing PyTorch's softmax implementation, you now have a complete blueprint for multi-class classification.